稍等。哦，可以开始了。
Good afternoon, everyone. My name is Shengyao Lu. I'm an assistant professor in the Department of Computer Science at the University of Victoria. Today, I'd like to talk about something that sits at the intersection of structure and language, and why this intersection matters more than ever. Let's start with a question. What do we wish the AGI to do? The AGI means artificial general intelligence, which refers to the human level of AI or more on most tasks. For sure, we don't eventually want AI to be like this, right? Instead, we want the AGI to do all of our work without needing to eat or sleep. For example, helping us doing math, helping us doing the self-driving and analyze medical images, to help us with the patients and become an AI tutor to help us to educate the juniors or the students or the kids, children, and also help us to make games, and then we can directly play the game without wasting time to making it, right? But why do we view the graph language system as the next key innovation? Over the past few years, large language models and other foundation models like GPT series, Gemini, Claude, DALL-E, Sora have shown remarkable fluency in text, astonishing creativity in image generation, and impressive versatility across tasks. However, beneath this success, there lies a gap. The world is not made of sentences alone. Much of real-world knowledge is relational, structural, and interconnected. In other words, graph-shaped, such as the chain of robot behavior, such as the social networks and the molecular graphs, the AI network architectures, and the communication networks, and so on. So the question I want to explore today is simple but fundamental. What would it take for AI systems to not only speak in language, but also think in graphs? Moreover, current language models often operate as black boxes to hallucinations and unclear reasoning, which is what the explainable AI aims to address. Graphs, such as knowledge graphs or other relational structures, offers a way to organize the information into entities and relationships, providing a form of structured reasoning that is inherently more interpretable. The promise of marrying these approaches is to get the best of both worlds. The semantic understandings and generation capabilities of LLMs, augmented by the precision and transparency of graph-based knowledge. Recent survey also put it succinctly. Integrating knowledge graphs with large language models can enhance accuracy, reliability, and interpretability in AI applications, and addressing key limitations of each alone. Why this integration timely now? In the fields like question answering, the factual accuracy and the reasoning are critical. The LLMs alone sometimes make up facts or fail on complex multi-step reasoning. Graphs, by contrast, can store verified facts and explicitly represent connections. For example, a biomedical knowledge graph linking diseases or to genes. If we combine this, an AI system could reason through the graph for factual checks or multi-hop logic, while using natural language to understand queries and explain answers. Structured reasoning using the graphs grounds the models in reality, and the explainable AI, which is also called XAI, techniques can use this graph structure to show how a conclusion is made. These address a pricing needs. As AI systems becoming more and more powerful, we need them to not only to just give answers, but to justify and explain them in human terms. Graph language systems offer a path towards this goal, allowing AI to show its work in a human comprehensible way. For example, by setting a chain of relationships or subgraphs that led to the answers. Apart from the connection between language and graph, let's further review the core dimensions of general artificial intelligence. I view there are 5 core dimensions of AGI, where the first one is multimodality, referring to the ability to perceive and integrate information from multiple sources, such as language, vision, sound, action, and structured data. The second one is memory and continual learning, refers to retaining and updating knowledge over time, learning from new experiences without forgetting the old. And the third one is about reasoning and planning. We want to draw logical inferences and making multi-step decisions and planning towards the goals. The first one is called self-reflection and self-correction, where we monitor its own reasoning of the AI systems and detecting the inconsistencies in between and revising the errors. The last one is social and value alignment, where we want to understand human intent, emotion, and ethical norms, and cooperating within social and moral context. Why these 5 dimensions matter is because, for example, the modality, it gives AI a grounded understanding of the real world, not just text or just symbols. It connects perception with reasoning. And the memory and continual learning enables growth and adaptation. Current large language models are largely stateless and cannot accumulate knowledge like humans like us. And the reasoning and planning will move AI beyond pattern recognition toward causal and goal-directed intelligence. As for the self-reflection and self-correction, it's the core of metacognition, where we can build reliability, accountability, and scientific rigor. In terms of social value alignment, it ensures AI behavior aligns with human values and remains beneficial across cultures. Let's review the current progress and the gaps along these 5 dimensions. For the modality, models like Leap, Flamingo, GPT-5, AudioPalm, and Sora already combine vision, language, speech, and video. However, we still lack a unified world model that integrates structured knowledge such as graphs with perception. For the memory part, external memory and retrieval augmented generation, aka RAG, has helped large language model to recall facts. However, there is no true long-term or continual learning model yet, and models cannot build lasting and evolving the knowledge. In terms of the reasoning, the techniques like the chain of thoughts and tree of thoughts and some techniques built upon those methods have improved step-by-step reasoning. However, they are still limited to short-term or linear reasoning, and they lack the doable structured reasoning over graphs or rules. In terms of the reflection, there have been emerging methods such as self-consistency, React, and reflection allows partial self-correction. However, there are still no stable metacognitive loop. Systems can't systematically detect and correct their own reasoning flaws. And at the alignment side, reinforcement learning from the human feedback, aka RLHF, and constitutional AI has aligned output with the human preferences. It has already had this ability. However, there's still no deep understanding of the values or context, and limited cross-cultural or ethical generations. In short, in the dimension of multimodality, we have vision language and speech language models, but we're still missing graph language models. And for the memory side, we are able to borrow the external memory for retrieval, but there is still no true continual learning. And at the reasoning dimension, we have short-term and linear reasoning, but we don't have doable structured reasoning. In the reflection side, we have the partial self-correction, but we still lack stable metacognitive loop. At the alignment side, we are able to align output with human preferences, but like the cross-cultural or ethical generations are still limited. In summary, like why the graph language system is so important is because current AI systems have been good at generating the text, images, audios, and videos in a controlled way and holding like fluent multi-turn conversations and following the instructions and adapting across tasks using the field shot or like supervised fine-tuning with their like broad word knowledge. They are able to understanding and describing the images in a fantastic like performance. However, they still lack the capacity of understanding and manipulating graph structures, like performing the structured and multi-hop relational reasoning and generating structured output like graphs or symbolic plans, or correcting and revising its own logical mistakes. Therefore, advancing graph language integration can extend multimodality into structured domains and provide more coherent memory, reasoning, reflection, and graph language alignment. Eventually, we want AI that can reason over structured knowledge like a database or knowledge graph and converse in natural language with built-in explainability. And this would mean AI assistant that can answer complex queries with the rigor of a knowledge base and the flexibility of an LLM or scientific discovery system that propose hypotheses together with interpretable evidence trials. And structured graph act as the minds of logics and the language as a voice. Together, they could overcome many limitations that current AI have. With the motivation in mind, let's first take a look at the success story in AI, where the integration of the vision and the language. This will show how the two different representations, such as like the images and the text, were combined to great effect, and it will set the stage for where we hope to go and the graphs and for the graphs and language. Recall that we have mentioned current AI systems have been good at understanding and describing the images. What can we learn from there before we actually develop our fully effective graph language systems? Why vision language are successful? Why not like graph language? What are the challenges like there? Vision language model. Here is what is a vision language model. Vision language models are broadly defined as multimodal models that can learn from images and text. They are a type of generative models that take image and text input and generalize like text output. Large vision language models have good zero-shot capabilities, like the example shown in this figure at the top right corner. They can generalize well and can work with many types of images, including like the documents, like as shown in the figure right here, the documents like the web pages and more. And the use cases including like chatting about images, like image recognition, will use these instructions and visual question answering and document understanding, image captioning, and others. Some vision language models can also capture like spatial properties in an image. These models can output bounding boxes or like segmentation mask when prompted to detect or segment a particular subject, where they can localize different entities or like answer questions about their relative or absolute positions. There is a lot of diversity within the existing set of large vision language models, the data they were trained on, and how they encode images and assess their capabilities. The entire trajectory of vision language framework illustrates the potential of such integration. In that parallel domain, research have converged to a practical three-part pipeline, where the first one is vision encoders provides a robust image representation, and the second one is cross-modal aligners and which bridge visual content with textual informations. And the generative models serve as executors that edit or synthesize images according to the prompt. This encoder, aligner, and executor trade has proven robust against tasks and scales in this domain, enabling models that not only interpret but also act, feeding generative feedback into representation learning. As an encoder, the vision transformer, which is also called VIT, proved that the transformer architecture, which has been so successful in the natural language domain, and everybody knows that, they have proved that the vision transformer could be applied to images without any convolutional layers. VIT treats an image as a sequence of patches, like the 16 times 16 pixel patches, and process them with self-attention, just like words in a sentence. The result was state-of-the-art image classification performance, showing that a pure transformer can also achieve a very good performance at the vision tasks. VIT success matters for multimodal AI because it means we could have a unified architecture for text and images, a crucial step towards combined models. The cross-modal aligner can further help to bridge the visual contents and textual instructions. The model called CLIP was trained on 400 million image-to-text pairs from the internet to directly connect the visual features with natural language descriptions. The model learns to produce a high-dimensional embedding for an image and for a text caption, such that the correct pairs are closer together. With this joint embedding space, you can do zero-shot image classification and retrieval, and the model can recognize objects in images just by being given the text labels without any task-specific training. For example, the CLIP model can take a random photo and decide whether it's more likely to be described as a dog or a cat by marrying similarities to those text prompts. This was impossible before. CLIP actually opened the floodgates to many new use cases by providing a general bridge between the vision and language. Its robustness also highlighted the multimodal training on raw web data and can yield very general and powerful models. An exciting recent development is open source, like vision language chatbots, like Lava, which is the full name is called Large Language and Vision Assistant. Lava connects pre-trained vision encoder, for example, the one from CLIP, as a visual backbone, to a large language model with some additional training. In Lava's case, in total, 158K image question answering samples generated by GPT-4. Like the Lava system can answer user questions about the images in a conversational way. And essentially, it's like giving an LLM set. And this matters because it takes the general reasoning ability of larger models and grounds it in a visual world. Lava and similar models, for example, the OpenAI's GPT series, a vision can analyze an image and carry on dialogue, for example, describing a scene and answering follow-up questions about it. This general purpose, multimodal capability, is what we ultimately want for graphs and language too. And the last one is about the generative models. Perhaps this is the most successful vision language system that we have been made in the past years. Like OpenAI's DALL-E showed that AI can create images from text descriptions. It wasn't just simple click art. DALL-E could produce novel, often fantastical images by combining just concepts. A famous example was a prompt, an armchair in the shape of an avocado. And DALL-E produced several plausible, even stylish images of avocado-shaped chairs, a concept that is extremely unlikely to have seen before. And this demonstrated a new level of compositional creativity. The model understood the words and how to merge their visual attributes in a realistic way. And Stable Diffusion took this further by open sourcing a high quality text to image model, which sparked a huge community and countless applications. And in recent years, we even have text to video. OpenAI Sora is a model that generates short videos from a text prompt up to a minute long. For example, you can prompt Sora with a drone view of waves crashing against cliffs at sunset, and it will attempt to generate a vivid video exactly that. That's how we made success, like in the vision part. Nowadays, we are able to use the generative vision language models to edit or synthesize images or like even videos according to the prompt so smoothly like this, like shown like this with several prompts and an image. You can get more as your following your instructions, following the user's instructions. And looking back at this trajectory, there are a few key takeaways relevant to our graph language topic. First, large-scale pre-training on paired data, such as like the image and text, was a game changer. For example, Clip's 400 million like image to text pairs gives it like the ability to connect the modalities. Second, the architectural innovation to fuse modalities like the flamingo's interleaved context or Lava's simple connector between the vision and large language models. These have enabled the system that can like smoothly interact in both modalities. Thirdly, adding a generative component also make the entire system become more creative and make it be able to apply to more new applications. We will see like the same scene comes up when we discuss the graphs and language. We will ask, do we have a similar model as Clip for graphs? How do we fuse the structured knowledge with this text? Can we generate graphs or like knowledge like DALL-E generates images? Something like that. Now that we have seen what have been achieved by combining the vision and language, let's discuss the current state of graph language research. We will see that we have some pieces in place, like methods for like graph to text or text to graph, but still some gaps, which sets the stage for the new framework that I will introduce afterwards. When we actually shift from the images to the graphs, there's no comparable graph language pipelines yet exist. At the encoder side, do we still have like we have a lot of questions lies there in terms of the graph encoder? Our current graph encoder robust enough for the graph representations? Are the current do we currently have a cross-model aligners that can bridge graph contents with textual instructions? And at the output side, do we have an executor that can edit graphs according to the prompt? And can we achieve structure-enhanced reasoning and planning like nowadays? First, we do have some challenges when we shift from image encoding to graph encoding. Images and graphs differ fundamentally in their data form. Images are continuous 2D grid of pixels. However, graphs are discrete topological structures composed of nodes and edges. They also differs in representation geometry. Image feature lies on a regular Euclidean grid, whereas like graph features are defined over non-Euclidean structures requiring. For example, with these three values of red, green, and blue, we are able to obtain this color. We are able to represent this color. And these values are actually like continuous from 0 to 255. Of the graph, like we do have a feature, a property called permutation invariance, where when we swap the order of the nodes, the graph doesn't change at all. But if we swap the order of an image, for example, the first piece, the first piece and the last piece, then like the image will be no longer like what it was. Like I will also say that I got something that I need to mention in this slide. The large vision models have the good zero-shot like abilities. However, it's here. Like the permutation encoders, the images carry continuous signals on a regular grid, whereas graphs represent the discrete rational structures with the symbolic and learn node features, or like what I just mentioned in the examples. And currently, in most practical scenarios, we encode the graph using message passing graph neural networks. Each node updates its representation by aggregating information from its neighbors. Like for example, here, and this process can be repeated layer by layer. This is currently the dominant paradigm for graph encoding. I will take this for example. For example, for node 1, for this node 1, a graph neural network at one layer of a graph neural network, we will firstly collect the message, which is actually the node feature of node 1, and then we collect the message from all the neighboring nodes, such as node 2, node 3, and node 4, and then we algorithm together and update the embedding of node 1. And after one layer of GNN, it becomes like this. We do that for every single node in this graph. So all the embeddings of nodes are changed. By iteratively do this, like we incorporate the message that is several hops away from each node. GNNs do not produce ordered embeddings the way the vision models do. Applying a vision, this is because like applying a VIT style transformer directly to a graph would break the permutation invariance, but they still face some fundamental will break the permutation invariance, which is one of the most essential property of the graph data. However, modern graph like transformers may have introduced some like special structural encodings to preserve the permutation invariance, but they still face their fundamental challenges. For example, lack of the natural positional structure, or like limited ability to capture deep relational or symbolic patterns. And due to this nature of graphs, we also have challenges in graph language alignment. Language or text data are inherently one-dimensional, so the embeddings are naturally sequential. For example, the text are sequential, then the token are sequential. And when you feed it into a large language model, the embedding, the token embedding outputs are sequential. These embeddings are just connected together and sequentially. And to align with other modalities with language, we often have to linearize them. For example, as what we have did in the vision transformer, like although the image data are two-dimensional, like the pixels follow a consistent spatial order, which allows us to flatten the image patches into sequences like this. But for the node embedding learned from the GNNs, permutation invariants must be preserved, and forcing them into a sequential form would break this property and introducing some structural bias. And even with some advanced stuffs, like you will still have to follow some orders. Yeah, so for a cross-model aligner, the node and graph representations from GNNs are not robust enough to accurately align with language models. How about at the output side? At the output side, there have been a lot of work that try to perform structured reasoning for large language models from both externally or internally. At the external side, they use external database or tool for graph level knowledge retrieval. What they actually have done was to retrieve key information from the knowledge graph, which is also known as KGs, to ground large language model reasoning in structured data. The shortcoming of these models are they cannot update the database in real time or dynamically during the interaction or during the conversation between the agent. And they usually only one-time lookup per question and lacks the state tracking or iterative brainstorming for these external methods. And at the internal side, they usually do a pseudo-structured thinking where they explore more thoughts from some arbitrary nodes. When you are having conversation, when you chat with an agent, they create a node after the answer you a question, they give you some thoughts, and these works are proposed to explore more thoughts based on the conversation, to develop more nodes from arbitrary ones and delete the bad ones and merge the related ones. The shortcoming, the disadvantages of these works are that they still enforces a direct acyclic graph of reasoning steps rather than a fully arbitrary graph. The direct acyclic graph are more like a tree instead of the true graph, right? And the thought tree is tied to a single reasoning run and disappear after the completion. Also, they lack a deep they lack a deep backtracking algorithm where they mentioned the backtracking here, but what they have actually done was to, when they find one node is bad, they will just go back one step. They lack a backtracking algorithm that can go back all the way down, even to the input. So in summary, at the output side, the current graph language pipeline, they try to externally borrow from knowledge base or internally mimic the structured thinking using the DAG, but there is still no true graph language interactive paradigms. So I would say, let me introduce one framework that proposed by us. Our research made a step towards a next generation of graph language system. It's called R5, Rule Discovery with Reinforced and Recurrent Relational Reasoning. It combines the concepts of explainable AI, the reinforcement learning, and the backtrack rewriting algorithm, and merge and infer. It does merge and infer using a dynamic rule memory. Let me introduce how it works. The big picture is this: R5 is a graph language architecture that's centered on iterative relational reasoning with memory and self-corrected baked in. The goal is to address the gaps we just discussed by enabling an AI to reason, to reflect and refine its reasoning over graphs, all while engaging in natural language. Imagine an AI agent that when we ask a complex question, can first represent the relevant knowledge as a graph structure and also reason over that graph to find an answer and reflect on whether the answer seems plausible or if the contradictions exist. It can also refine its approach if needed, or for example, explore different paths in the graph or add a new pieces of information and finally respond with not just the answer but an explanation with the rule they have been used to draw the conclusion. Like, let me introduce the background of this work. Well, most AI researchers were focused on improving the performance of the sequence-to-sequence supervised learning models by tweaking the network architectures and increasing computational resources more and more. Like, the reasoning and planning aspects of AI were largely overlooked. Instead, we began to exploring whether AI models could extract underlying rules from the data, combining the short rules like this to form longer ones, or infer rules from short ones. And with these combined and inferred long rules and short rules, we are able to improve the performance of the original model and the dataset of the entire task. Here is a straightforward example of how we do the infer and combine. For example, if we have this graph A, we have that if I am Y and my sister is Z, sister's mother is X, and X is also my mother, I can extract a rule from this graph, which is rule A. My sister's mother is also my mother. And similarly, from graph B, we are able to extract that my father's mother is my grandma. And by saying combining, we mean that given just rule A and B, we are able to combine and conclude rule C, which is my father's sister's mother is my grandma, which we can extract from graph C. And by saying inferring, we mean that if we only have this graph C and graph B, and we extract the rules from there, we are able to directly obtain rule A without even looking into this graph A. But how can we do that? How to extract the rules, and how to combine the rules iteratively, and how to infer the rules iteratively? We actually use reinforcement learning for help. Yeah, here is a example of our R5 framework. I would say in this framework, let's consider the problem formulation like this. We view the states as nodes, with the red nodes as the initial states and the green nodes as the goal states. And our aim is to find the edge in between, and the solution should connecting the two. For example, if the red node is how much is 1 plus 1, and the green node is what is the result, and the edge is the 2, should be viewed as a solution. In our model, we firstly convert a natural language questions or story into graphs, into a relational graph, and then we sample chains of relations between the initial states and the goal states. Then we encode them into the embedding of all relation pairs, like shown here, and feed it into a self-play reinforcement learning framework where we use a policy value network guided by a Monte Carlo tree search that outputs a relation pair. For example, this relation pair referred to the relation pair out here. And then we select this relation pair and merging to a new relation. And after merging, the relation will be like this. Here is an example of the resulting chain of relations. And after iterative merging, we eventually got just one edge between the initial state and the goal states, and it will be our answer. Since this policy value network and Monte Carlo tree search only give us a relation pair, but our action is to merge it into another relation. So we need to lend a hand from a dynamic rule memory, where we look up rules for an action. We look up this key. This relation pair will become a key, and we will find the corresponding value from the rule memory to obtain the relation that we aim to merge to. And after iterative merging, we will save all the chains of actions to the dynamic rule memory. And in the meantime, we will drop like bad rules that are shown to be wrong when we check with the training data. This model gives us like the possibility to iteratively combine the short rules and decompose long rules to short rules with relation X, and infer the short rules when more long rules comes in. A more clear example on the dynamic rule memory is like this. For example, if we have this as an action, the first two relations are the key, and we will look up this from the dynamic rule memory. For example, we look up and find it's here. Then we know that this relation pair should be merged to R21, and this becomes the action that how we actually do on the graph. For example, like the graph here, like after the graph was originally like this, and after finding these two relation pairs, the relation pair should be merged to R21. We add another edge on the original graph like this. If a relation pair is not in the memory, then it should be replaced to an invented relation that has not been used, and this should be memorized as a rule in the dynamic rule memory. For example, instead of a certain rule R21, we will view it as U1 or like U0, something like using different index, where we mean this is not a known relation, but we may know that later. We will just leave it for now. Something like that. And this during the training at the end of an episode, R5 will check whether the obtained relation matches the answer in the data set. If not, we will need to update the dynamic memory with the backtrack rewriting algorithm described here, where we actually like go all the way like down to the input, rewrite everything like along the path. And here is a more straightforward example with the invented relation here. Consider this is just a toy example with input graph X here and Y here. We firstly enumerate passes, relation pairs, a chain of relations like between the initial state X and the goal state Y, where we have two paths, R2, R0, R1, and R2, R0, R2. And then we encode it into the embedding of like relation pairs like this. The relation pairs will based on some like predefined features similar to this, but we have more like in reality. And then like we feed it into the self-play RL like framework that as I just mentioned before, and it output an action R2, R0, and we look up it from the rule memory. We find it here. Although it gave us like an unknown relation, but we will still like perform this merging, and now the path will be like this: U R1 and U R2, and then we may perform another round of like action sampling, and I'm sure that like the model will actually select U R1 as the action, and by looking up the dynamic rule memory, we will find that this relation pair should be merged into R0. and eventually we will know that the relation between x and y is actually R0. And the result is like this. We perform experiments on both like clean data sets, Clutter, which is actually a natural language data set where they convert the natural language story into graphs, into kinship graphs, and all the samples are correct. The inference paths of the training samples are just 2 or 3 hops, but like 2 or 3 hops, or like for table 3 and table 11, like the training stories are just of length 2, 3, 4. But like the inference paths where we perform our testing are actually 4, 5, 6, 7, 8, 4 to 10, or like 5 to 10. Namely, we train on small scale tasks and generalize to larger tasks. These can test like our aim of combining rules. And the results shown that like our work has been much better than the previous work, including like the convolutional networks, or like the graph neural networks, or some like symbolic methods. We also did some experiments on some like noisy data where like the length of the model actually mixed. Sometimes you will have like longer, very super long like rules, and sometimes like the rules can be really short, but they are combined. And in most cases, you will have to perform some degree of inference where you have multiple instances from the training data where the inference paths are so long, and you store like the entire inference path by our like invented relation, and then eventually we have to like make prediction on the problems where the inference length is super short, for example 2 to just 3, and the results also give us like we have performed better than the existing methods. But the difference from this, from this clean data set one, are that since there are more noise in this data, we were not able to achieve like full accuracy, but we do have like very high rule recall rate. Yeah, I think that's all my like work for today. That's my talk for today. I'm currently recruiting masters and PhD students for like the fall 2026. If you are interested in working with me as a master's or like PhD student, feel free to send me emails, and we can sit and discuss to see if we have like good fit for you related to the graph, either the graph level explainability, or like the combining between the large language models and graph neural networks and graph representation learning, and perform graph language alignment and things like that. Thank you. I'm happy to take questions here.
Okay, thank you, Professor Lu, for the amazing presentation. So we're now open for the floor for questions from the audience. So please drop your questions in the live chat. Okay, the first question we have here is, in today's LLM architectures, which specific capabilities do you believe are truly irreplaceable without graph structures?
Truly replaceable?
Yeah.
Sorry.
Yeah. Irreplaceable.
Irreplaceable.
Yeah.
I think it would be like the broad knowledge. First, it would be the broad knowledge, as I summarized at the beginning of here. Yeah, first, I think that's a very good question. If something can be replaced by the graphs, then we no longer need the text, right? But there has to be something that is irreplaceable. I think the most important one is actually the ability to chat, to holding the fluent conversations with the users. because like in our daily life, we usually chat with each others using language, but not using graph. If you consider like two people are sitting together and you like hand in a graph and the other one hand in a graph, can they actually communicate with each other? No, they can't. So I think the most important thing or like the features that language have is actually the ability to holding interactive interface between the users, and graphs can actually help to enhance or like make the conversation or like making the entire system more reliable and more convincing. Yeah, that's what I think. Do you like these answers, or you have like any opinions? You can continue to ask questions, follow-up questions. Yeah, I'm happy to take them.
Okay, thank you. Let's see. The next question here is, which real-world applications do you think are most likely to benefit first from graph language systems?
I believe would be healthcare. Again, that's a very good question, and I believe that would be healthcare part, as like we have like a lot of current. Oh, I will go back to this page. We got a lot of like data, healthcare data. For example, the molecular graphs. For example, like the biology graph, biology data sets. We got a lot of graphs of that, and I already see like a lot of researchers is currently doing their projects or like a research program on this domain. So when they try to combine like the graph and languages, I would see they will use those already publicly available like molecular healthcare data sets and do experiments on those like data. So I will see a rapid boom on those tasks in like next few years. This is one side, and there may be another thing that about explaining the large language models, because like all the researchers, I mean like trying to, not all the researchers, I wouldn't say that word. It's like most of the researchers like doing this graph and language alignment and doing like the graph language system, doing this integration. They are most of them are from like the computer science domain or like the statistic domain or like the math domain. They are AI researchers and they are more familiar with the AI architectures. So I think this is similar to like when the AI comes, when the large language model comes, like the coders, like the software engineers, are the first that can be replaced. So I think the AI network architecture can also be the first that can be firstly fully understand and explained, and then after that we can we will like the researchers will actually like develop or like expand their research from like the AI domain by firstly explaining the AI network architecture and then slowly to other domains. I think this is also a possible trend. Yeah, I think those two areas are the stuff that are maybe firstly addressed or solved. Yeah. Is there like any other or like the third questions here?
The last question we have here is, do you believe future large models will need a dedicated graph module, just similar to how current models include a vision module?
I think we need that. We definitely need that. Because like nowadays, like most of the data are represented by graphs, but now we cannot handle them at all. If we do not have like a cross-model aligner that can align like the graph models with the large language models, how do we solve those real life problems? I would say definitely yes. Yes, we do need that. We do need integration, effective integration between the graphs and languages. Yeah.
Okay, thank you. I think that brings us to the end of today's session. So huge thanks again to Professor Liu for sharing her expertise on graph language systems and her vision for the future of reasoning AI. We'll share our play and slides on our community channels, so stay connected on Discord and Telegram. And most importantly, don't miss the next episode of the AI Coloring program. Thank you guys. Bye.
Thank you. Bye bye.